All right, let's get started. So before I jump into the clustering or the contents of today's workshop, let me give you guys some background. The modern applications need accelerated computing. So far, we humans have accumulated petabytes scales of data. And how much is a petabyte? There are 28 zeros after 1. And we have built like massive models so far. Some of the large language models have up to hundreds of billions of parameters. And all of the applications require real-time or near real-time executions. Some examples include the recommender systems, large language models, forecasting, fraud detection, genomic analysis, and cybersecurity. And on the right-hand side, the single-threaded CPU performance is indicated by the blue line. It's been growing at 1.1 times per year, and the scaling traditional CPU-based systems is not sufficient for today's workloads. And the green line indicates the GPU computing performance. It's been growing at 1.5 times per year, and by 2025, the GPU are expected to deliver 1,000 times speed up compared to the past. So what are the benefits of GPUs? It has parallel computing, a higher throughput, and better scalability. And we want to do a CPU versus GPU comparison. The difference in capabilities between GPU and a CPU exists because they are designed with different goals in mind. While the CPU is designed to excel at executing a sequence of operations called a thread as fast as possible, and can execute maybe up to a few tens of these threads in parallel, the GPU is designed to execute thousands of them in parallel. So the GPU is specialized for highly parallel computations and therefore designed such that more transistors are devoted to data processing rather than data caching and flow controls. The schematic figure shows an example distribution of the chip resources for a CPU versus a GPU. Let's talk about machine learning. So in machine learning, we often categorize algorithms into 3 primary types: clustering, classification, and regression. Let's briefly highlight the key differences among them, and we'll dive deeper into clusters. Clustering is an unsupervised learning method. It's being used to group similar points together based on the underlying patterns and the characteristics. Some common algorithms include k-means, DBSCAN, HDBSCAN, agglomerative like clustering, and some real-world applications include customer segmentation, document clustering, and topic modeling, and anomaly detection. And the second type is classification. It's a supervised learning, as it has the label data, and it's used to predict distinct labels or categories. Some common algorithms include logistic regression, random forest, and support vector machines, and it's been commonly used in image recognition and fraud detection. And the last one is regression. It's a supervised learning method as well. It's been used to predict the continuous numeric values. Some common algorithms include linear regression, ridge regression, or lasso regression. Some real-world applications include price prediction and demand forecasting. And for the purpose of this workshop, we will focus specifically on clustering. From the practical and use case perspective, I would like to briefly introduce 4 clustering: k-means, DBSCAN, HDBSCAN, and Gaussian mixture models, GMM. First, k-means is one of the most widely used algorithms. It's particularly effective when dealing with simple, clearly defined clusters. And next, we have DBSCAN. Unlike k-means, it does not require you to have a predefined number of clusters, and it's very good at taking care of the noise. And also it can detect arbitrary shaped clusters. Some use cases include geospatial clustering, anomaly detection in network and security logs, clustering biological and or scientific data. And the next one is HDBSCAN, which excels at clustering data with more complex structures or significant noise. It's super robust in handling outliers and the noise. And some use cases include wildlife habitat mapping, healthcare fraud detection, social media analytics. And the last one, we have Gaussian mixture models, GMM, which provide probabilistic clustering. Instead of assigning the data point strictly to only one cluster, the GMM assigns probabilities of each data point belonging to each cluster. This feature makes it ideal for scenarios where there's an overlap between clusters or uncertainty in the data. For today's workshop, we will focus on k-means DBSCAN and HDBSCAN. And before we jump into the clustering and their algorithms directly, I would like to introduce the dimensionality and visualization tools as well, because we wanted to reduce the dimensionality of the raw data in order to build the clustering. Also, we would like to visualize the clustering results. So here I'm introducing 3 different dimensionality reduction and visualization tools: PCA, Principal Component Analysis, T-SNE, and UMAP. On the left, we have PCA. Is a fast linear compression that preserves the global variance. Because it preserves the global variance, so basically it will break down the global structure and the local structure through some very complicated mathematical computations. Therefore, it's not recommended for data visualization. However, it's a good tool for dimensionality reduction. Some use cases include pre-processing step for machine learning and feature reduction. And the second one is T-SNE. T-SNE is a nonlinear visualization of local structure in high-dimensional data. It's pretty good for visualization as it preserves the local structure. And some use cases include visualizing clusters in word or image embedding, exploring structure in genomic sequential data. And the last one is UMAP. UMAP is a fast and scalable nonlinear projection preserving both local and global structure. Yes, it's very good for visualizations as it can preserve both local and global structures well. And some use cases include large-scale embedding visualizations, for example, BERT, visual analytics of high-dimensional data, exploratory data analysis, and feature discovery. And I'm going to talk in depth of each of them. The first one I want to talk about is PCA. PCA is short for Principal Component Analysis. Its algorithm is through a fairly complicated mathematical computations, but if you have the formula, it shouldn't be too hard to compute on your Python. The first step is to standardize the data. We usually center the data with the mean value of 0 and optionally scale it with a unit variance. And then we compute the variance matrix using the formula on the screen. And afterwards, we calculate the eigenvalues and the eigenvectors. And in the first step, we sort eigenvalues by the eigenvectors by the eigenvalues. So basically, you compute the eigenvalues and eigenvectors, and if you are interested in the first 10 principal components, you will go to find the highest 10 eigenvalues and find their corresponding eigenvectors. And then you project data onto the 10, for example, principal components using the formula here. And all of the 5 steps can be GPU accelerated using cuML. For example, when we are standardizing the data centering and scaling use GPU matrix operations. And in step 2, when we compute the covariance matrix, the GPU-accelerated cuML use fast matrix multiply kernels. And in step 3, when we calculate the eigenvalues and eigenvectors, we can use cuSolver and cuBLAS, which are two cu.x libraries. As of the key features of principal component analysis, first of all, is linear dimension reduction. Second, it's orthogonal transformation, meaning there is no multicollinearity among the variables. And the third one is variance preservation. Some good use cases include exploratory data analysis, EDA, pre-processing for machine learning, and noise reduction. It has the below advantages. It will reduce the dimensionality while preserving the most variance. In other words, it preserves the most of the information of the original dataset. And second, it improves computational efficiency for downstream tasks. And the third one is like you denoise data by discarding minor components. Like for those low variance or noise, you are just eliminating them. Some disadvantages include it assumes a linear relation, and it has a poor cluster separations. It has a loss of local structure. Here I'm providing a code snippet for principal component analysis on CPU. So first, we load the data and extrapolate it by 1,000 times. So the data set size could be 1 million. And then we reduce the dimensionality to 10 dimensions and to 20 dimensions by specifying n_ components to be 10 and 20 respectively. Then we plot out the results. As you can see from the picture on the right, the execution time is roughly 4 seconds for each of them. And the bar chart, the first 10 principles on the second bar chart are identical with all of the principal components from the first bar chart. Talking about the acceleration for PCA with NVIDIA cuML, it has certain key features. It's GPU accelerated, so it's super fast. It's highly scalable, so it can take up to millions to billions of dataset for machine learning. And it has a seamless integrations with the existing Python frameworks such as NumPy, Matplotlib, and scikit-learn. And it has the same API with the traditional CPU-based scikit-learn. So meaning transitioning to GPU acceleration is very straightforward, requiring minimal changes to your existing code or syntax. The last one is end-to-end GPU workflow. It allows data scientists to remain entirely within GPU-enabled workflows, reducing the bottlenecks when moving data between CPU and GPU memory. And if you look at the code snippet on the left, with all the code the same with the previous slide, the only difference is you add a loader, a cuML drop-in on the top, %load _ ext cuML.xl is the loader and also the activation for NVIDIA cuML. We are currently at the beta version or beta test. There is certain limitations for the zero code change. The limitations are all documented in the link here. If you are interested in looking at the limitations, you can refer to this URL. And let's talk about the execution time. On GPU, it takes less than 1 second and 2.73 seconds respectively, compared to the CPU execution time of 4 seconds. It's much faster. Okay, now let's get started with your PCA notebook. I'm going to give you 15 minutes on this. I'm going to count the time. And actually, before you get started, so after you work, you're done with this workshop, after you get back home, if you want to work on the RAPIDS cuML in your Google Colab, for example, on your own machine, here is a package installation guide. You go to the URL on the bottom left corner, and you choose your preferred release, method, system, CUDA, and packages. And you can copy the command and paste it on your terminal, on your Jupyter, and it should get started. And afterwards, you go to your notebook. You are going to load your cuDF pandas so you can perform some GPU-accelerated data operations. Then you, at the drop-in on your cuML, you should be able to start the GPU-accelerated machine learning. And all the rest of the library import command remain the same. Are you guys all able to get into the notebook? No. No. Let me take a look. So it might take you guys a little bit time to load. So I think it's best for me to give you a walkthrough of the PCA notebook. So the first section is about the initial environment setup. Basically here we are testing if the cuDF pandas working, if the GPU acceleration working fine. Then afterwards, I'm providing the code snippet on the CPU PCA. So then afterwards, I'm providing the same code snippet for GPU PCA. Like I said, all the code remain the same. The only difference is the cuML dropping on the very top. That's the only difference you will see. Yeah, just want you guys to have a flavor of the difference in the execution time between CPU and the GPU. Looks like most of you are already done with the notebook. Maybe let's just wait for another 2 minutes and move on to the next section. We have a lot to cover for this workshop. Okay, probably we should get started with the next section. Yeah, let's talk about T-SNE. T-SNE is short for T-distributed stochastic neighbors embeddings. Its algorithms is like a nonlinear dimensionality reduction that models high-dimensional data into low-dimensional space by preserving local structure. It basically follows two main steps. The first step is similarity computation, and the second one is KL divergence minimization. For the first step, for high-dimensional space, we need to compute the pairwise distances in the original high-dimensional space, then convert these distances into conditional probability or similarity using a Gaussian kernel. And as for low-dimensional, like 2D or 3D space, we needed to compute pairwise similarity using a student T distribution with 1 degree of freedom, which is heavy tilt. And in the second step, when we are doing KL divergence minimization, we need to optimize positions of points in the low-dimensional space to minimize the KL divergence between the high-dimensional and low-dimensional similarity distribution. You don't need to understand this algorithm. This is just for your knowledge. In step 1, when we are doing similarity computation for high-dimensional space, we use GPU for faster, like k-nearest neighbor, KNN graph, or pairwise distances. Like for low-dimensional space, when we are computing pairwise similarities, we use GPU for all probabilities and gradient computation. As for step 2, we use gradient descent iterations running fully on GPU. Some key features of T-SNE include it's pretty good at dimensionality reduction and visualizations. It will capture the local structure. It's non-parametric and stochastic. Some good use cases include visualizing the word or image embeddings, anomaly detection and outlier visualization, reducing BERT or LLM embeddings for topic modeling. It has some advantages. For example, excellent at separating well-defined clusters in the low-dimensional space. It captures nonlinear relations between features and is effective for exploratory data analysis, EDA, and feature discovery. It definitely has disadvantages. It does not give you the picture of the global structure. is non-deterministic output, meaning it does not have a stable mapping functions. And there's no transform function, meaning you can probably fit x1, but you cannot use the result to transform x2. You can only do fit and transform the same dataset. And next one, it has the poor scalability. However, we can improve it with NVIDIA GPU. So here I'm giving you two examples of the T-SNE features, dimensionality reduction and clustering visualization. The example on the left shows how T-SNE projects a 498 dimensional data into two dimensions for visualization. And the example on the right gives you showcases how to use T-SNE to visualize k-means clustering results. I'm also providing an example of how T-SNE is combined with dimensionality reduction and clustering. So the raw dataset, we will perform the dimensionality reductions on the raw dataset. Then we will apply the k-means clustering onto the result, onto the reduced data. Then afterwards, we will use T-SNE to visualize the clustering results. And the code snippet gives you, shows you how to execute the workflows on the top. And on the right-hand side is the visualization result. It has been using the classic MNIST dataset. So on this slide, I'm giving you a CPU code snippet on T-SNE. First, we load the dataset, then we use T-SNE to reduce the dimensions to 2 dimensions, then we visualize the result. The execution time is 1 minute and 5 seconds. And with all the code the same, the only difference is the cuML drop-in on the top. We make the entire workflow GPU accelerated. It has certain advantages. It's GPU accelerated, so it's super fast. It's highly scalable. It can handle millions to billions of datasets for machine learning. And it has seamless integrations into the existing Python workflow or Python frameworks, including NumPy, Matplotlib, and scikit-learn. And it has been leveraging the same API with the traditional CPU-based scikit-learn, meaning transitioning to GPU acceleration is very straightforward. It does not require any code change to our existing code. And it allows end-to-end GPU workflows. It allows data scientists to remain entirely within the GPU-enabled workflows, reducing the bottlenecks that occur when moving data from between CPU and the GPU memory. The execution time for the GPU cuML is 6 seconds compared to the CPU-based T-SNE of 1 minute and 5 seconds is significantly reduced. Now let's work on the T-SNE notebook. I'm giving you 10 minutes to work on the T-SNE notebook. And probably it's best for me to give you a high-level walkthrough. First section, environment setup. Second section, give you a flavor of CPU T-SNE. It might take about 5 minutes to complete this execution on CPU. Then afterwards, we load the cuML drop-in on the top and start to work on the GPU T-SNE. It's going to be much faster. And lastly, I'm providing an example of how T-SNE is combined with PCA and k-means working. Yeah. So you have 10 minutes to work on this. If CPU T-SNE is taking you too much time to execute, probably you can just kill it and move on to the GPU T-SNE. But you should get a flavor of like the execution time difference between CPU versus GPU. And also, if you see some error messages, some very weird messages. It might be because you are overwhelming the GPU. So we all use different GPUs. When I'm creating this notebook, my GPU is A6000, which is much faster than a lot of the GPUs other people have been using. So if you can take a subset of your MNIST dataset, you may be able to avoid the error message. next piece is T-SNE. T-SNE is another pretty good dimensionality and visualization tool. It's short for Uniform Manifold Approximation and Projection. The algorithm is basically create a k-nearest neighbors KNN graph known as an all neighbors graph to build a fuzzy topological representation of the data, which is used to embed high-dimensional data into lower dimensions. It has several key features like dimensionality reduction. It's highly scalable. It preserves both the global structure and the local structure. And it has the parameters for flexibility, n neighbors and mean dist. N neighbors will control the global structure versus the local structure, and mean dist will control like how tightly UMAP want to pack the points together. Some good use cases include data visualizations, pre-processing for the downstream machine learning tasks. It is very good to provide a clarity of the clustering results, and it's an image and text analysis. It can interpret large, complex datasets to identify patterns in images, documents, or other high-dimensional data. And it has the below advantages. It captures the meaningful structure in the high-dimensional data. It is suitable for exploratory data analysis, EDA, and feature discovery. It produces interpretable 2D or 3D projections with better continuity compared to T-SNE. And if you look at the GIF on this slide, the two clusters may be very close to each other in the two-dimensional space, but could be very far apart in the high-dimensional space. Here you go. On this slide, I'm giving you two examples to demonstrate the two features of UMAP, dimensionality reduction and cluster visualization. The example on the left shows how UMAP projects a 4D data into a 2D for visualizations, leveraging the classic iris dataset. And the example on the right uses UMAP as a pre-processing step for the clustering. And again, I'm providing a CPU code snippet on how to use UMAP for visualization. I load the dataset. Then I reduce the dimension of the dataset to 2D and 3D by specifying n_ components to be 2 and 3. Then I plot out the results. It takes 22 seconds to execute the 2D visualization and 10 seconds to execute the 3D visualization. When it comes to NVIDIA cuML UMAP, from the coding perspective, you just need to load the cuML drop-in on the top, with all the rest of the code remaining the same. Again, some key features of the NVIDIA cuML is GPU accelerated, very fast. It's highly scalable compared to CPU. It has seamless integration to the existing Python frameworks like NumPy, Matplotlib, etc. It has been leveraging the same API with the traditional CPU-based scikit-learn. It allows end-to-end GPU workflow, so you can stay. You don't need to convert the data between CPU and GPU memory. And the execution time leveraging NVIDIA cuML is less than 1 second, compared to the CPU execution time of 22 seconds and 10 seconds is significantly reduced. And now let's work on the notebook for UMAP. Again, we are going to spend like 10 minutes on it. Yeah, as for the notebook, again, the first section is environment setup, second section CPU UMAP. third section, GPU UMAP. CPU UMAP and GPU UMAP have the identical code, with the only difference being the cuML dropping on the top.
Yep. Thank you.
I think I can get started with the next section. You guys are very fast. Great. Let's move on to the next section. So I have introduced the 3 dimensionality and visualization tools. maybe some of you may wonder the difference of them. I'm going to give you an in-depth comparative analysis on PCA, T-SNE, and UMAP. So first of all, PCA, Principal Component Analysis, is very fast and scalable. It will capture the global variance, but it's not very effective at preserving local structures. That's the disadvantage, because it goes through a very complicated mathematical computations. When it goes through the process, it basically breaks down the global structure as well as the local structure of the original dataset. So it does not give you a good picture of the original dataset. Therefore, it's not good for visualizations. You can still do that, but it does not give you a good picture. The second one is T-SNE. T-SNE will preserve the local structure, but not the global structure. Also, it's non-parametric, meaning it does not have a stable mapping functions. So there's no transform function supported for new data. Like you can fit into X1, but you cannot use the result to transform X2. You can only fit and transform the same data set. That's one of the limitations it has. The second limitation is it produces random and stochastic results. So if you run it multiple times, each time you run it, you get a different result. And it's computationally very expensive. The third one, UMAP. It can preserve both the local and the global structure. It's faster and more scalable than T-SNE. Some good use cases is like it can be used as an input for clustering, and it can also be used as embeddings for downstream ML tasks. I'm going to discuss that in details in the following slide. So for the purpose of this workshop, we would like to visualize the clustering results. So we got to pick between T-SNE and UMAP, and we prefer UMAP over T-SNE. The reason being is like T-SNE is not recommended to be used as a pre-processing step, but UMAP can be used as a pre-processing step. Also, T-SNE is not recommended for downstream clustering, but UMAP is. So why T-SNE and clustering is risky? T-SNE is optimized for visualizations, not clustering. It distorts the global distances. So some machine learning algorithms like DBSCAN and k-means may detect false clusters. It may give you the wrong idea. Also, the distance and density in T-SNE space do not reliably reflect the original data structure. As for UMAP, UMAP is better for pre-processing before clustering, and downstream machine learning tasks in structure-preserving embeddings. And it's better when handling larger dataset efficiently. And as you see, after you feed and transform the original dataset and get X T-SNE, it's not recommended to feed it into the downstream machine learning tasks to perform the fit and predict. But as for UMAP, you can feed and transform the original dataset into X UMAP, and it's recommended to perform the downstream tasks. And now let's start with the main contents of today's workshop, clustering. I'm going to introduce 3 different clustering algorithms. The first one, including k-means, DBSCAN, and HDBSCAN. The first one is k-means clustering. So while I'm walking you over the k-means algorithm step by step, you can refer to the GIF on the right. The first step is the initialization. So we randomly select the k initial centroids. And in step 2, we assign data points to the nearest clusters. Basically, we compute the distances between each data point and all k centroids. And then we assign each data point to the cluster of the nearest centroid. And in step 3, we update the cluster centroid. by recalculating the centroids by taking the mean of all points assigned to each cluster. And in step 4, we check for convergence. We check if the centroids have stopped changing or if the convergence criteria has met. And it hasn't been met, we repeat step 2 and step 3 until convergence. And among the 5 steps, step 2 and step 3 can be GPU accelerated. In step 2, when we assign data points to nearest cluster, the GPU can handle distance calculation in parallel. And in step 3, when we update cluster centroids, the parallel reduction algorithms efficiently compute sums across many data points at once. Again, I'm providing a CPU code snippet to, it's a GPU code snippet to visualize k-means clustering with NVIDIA UMAP. We start by adding the cuML dropping on the top, a cuML loader on the top. Then we randomly generate a 1 million dataset. And afterwards, we perform the k-means clustering using cuML, NVIDIA cuML. And afterwards, in order to visualize the clustering results, we reduce the dimensionality to 2 dimensions by specifying n components to be 3. Actually, it's a 3-dimensional, not a 2-dimensional. And we plot out the results. Let's work on the k-means notebook. I'm going to give you 15 minutes as it is a little bit longer than the dimensionality reduction tool notebook. So one of you asked me the question, how to identify the optimal value for hyperparameters inside each machine learning algorithm. Probably you can get a flavor from this notebook. Let me give you a walkthrough of the notebook before you continue to execute the notebook. So the first section is always the environment setup. We tested the environment and see if GPU acceleration is working properly. Second piece is we provide a code snippet for GPU accelerated k-means. And afterwards, I'm introducing a method called elbow method. This method is a technique used to determine the optimal number of clusters in k-means clustering by plotting out the within cluster sum of squares, WCSS, against the number of clusters. It's called elbow because the plot will give you an elbow shaped. And the optimal number of clusters is your elbow point. You can visualize it after you plotting it out. And afterwards, after you figure out the best number of clusters, you plot it back to your function. It will give you the best visualization result. And we have 30 minutes left. You guys do a great job. So I think we can move forward to the next section. It's faster than I think. Next one I'm going to talk about is DBSCAN. As I already mentioned at the beginning, DBSCAN is good at detecting arbitrary shaped clusters. Unlike k-means, k-means always assume the clusters are spherical shaped. And the DBSCAN is good at taking care of the noise. Some common use cases include geospatial clustering, anomaly detection in network and security logs, and clustering biological or scientific data. The algorithms, while I'm walking you over the algorithms, you can look at the picture on the right. It's actually not very complicated, this algorithm. So first we choose we choose parameters. Two parameters we need to pick, epsilon and mean samples. Epsilon is the radius of the neighborhood around a point. In this case, n are neighborhood. And mean samples is the minimum number of points required to form a dense region. In this case, m, we assume m equals to 4. And in step 2, we classify each point. We count how many points, including the point itself, fall within the epsilon radius neighborhood of P for each point P in the dataset. Then we need to classify the point as core point if the number of neighbors is greater or equal to the minimum samples. For example, the red point, it has like 1, 2, 3, 4, 5. It has 5 neighbors. That is greater than the mean samples of 4. So the red point is a core point. The second type of point is border point. The border point is not a core point, but still within epsilon of a core point. So the border point, it does not have at least the 4 points around it, but it's still within epsilon of a core point, the red point. So it's being considered as a border point. The last type is noise point, which is also outlier, like indicated by the orange point. It's not a core point and not within epsilon of any core point. And in step 3, we form the cluster. We start with an unvisited point. If it's a core point, we create a new cluster. And then we add all density reachable points to the cluster using density reachability. And we repeat for all of the unvisited core points. And the last step is label remaining points. So any point not assigned to any cluster is labeled as noise. All of the steps can be GPU accelerated. When we are classifying the point, GPU handles distance computation, epsilon neighborhood query, core point identification in parallel. In step 3, when we form clusters, GPU handles density-based cluster expansion with graph traversal using cuML, not in parallel. In step 4, when we label the remaining points, the GPU handles noise label in parallel. Here I'm providing the code snippet to visualize the clustering results using NVIDIA UMAP. We start by loading the cuML dropping on the top. And we randomly generate 1 million datasets. And afterwards, we perform the DBSCAN clustering. And we reduce the dimensionality to 3D using cuML UMAP, and we plot out the result. Now let's work on the DBSCAN notebook. Compared to k-means, DBSCAN is a little bit complicated. You cannot use elbow method to pick up the opti number of the hyperparameters. Therefore, we use a different approach. We use grid search together with the C-whole vector score to identify the optimal value for epsilon in this case. As you can see from the notebook. Okay, now I'm giving you, yeah, you guys are smart. You don't need that much time, so I'm giving you 10 minutes.
Running slowly.
Yeah, it may take a few minutes to even access from GPU. Okay, let's have another 5 minutes. So if you have problem loading it, executing it, or you think it takes too much time to execute it, you can always shrink down the sample size. For example, here, when I'm randomly generating the dataset, I'm generating 1 million dataset, but you can change it to maybe 10,000 or 100,000. And also for the grid search and SQL-wide score approach, we are running like 10 loops of DBSCAN you can always shrink it down to like 2 to 3. So it will only like run for 2 times. It can significantly reduce the execution time. Let's have another 5 minutes. Can we leave it running? Because we have better stuff to talk about later. Yeah, we have hyperparameter optimizations. We have bird topic to talk about. There are a lot of good stuff later. So let's just leave it running. Let me continue with this presentation. The next one we are going to talk about is HDBSCAN. It's probably the most complex algorithms. The HDBSCAN is even more robust in taking care of noise and outliers than DBSCAN. It's commonly used in wildlife habitat mapping, healthcare, fraud detection, and social media analytics. So while I'm walking you through this HDBSCAN algorithms, you can refer to the pipeline on this slide. The entire first row is step 1, when we are trying to build a minimum spanning tree of distance, MST. First, it computes the k nearest neighbors, KNN graph, where each point connects to its closest neighbors based on the mean samples parameter. Then it creates a mutual reachability graph. And finally, it builds a minimum spanning tree, so which connects all data points while minimizing the total distance. And in step 2, we do hierarchical clustering. HDBSCAN creates a hierarchical structure of nested structure. And afterwards, we condense the hierarchy. The hierarchical tree is simplified into a condensed representation. This step extracts the most meaningful clusters. And the next step, step 4, we extract the clusters. Once the hierarchy is condensed, HDBSCAN selects clusters based on their stability, clusters that persist over multiple density levels. And in step 5, we do convergence. The final step ensures that the cluster has stabilized and no further updates are needed. And all of the 5 steps can be GPU accelerated. In step 1, when we are trying to build the minimum spanning tree of distances, both KNN graph construction and MST computation are fully GPU accelerated. In step 2, the hierarchical clusters is optimized for GPUs using parallel tree structures, allowing fast computations. As you can see, we can do this step can be parallelized on GPUs. We can do different hierarchy clusters at the same time. And in step 3, the dendrogram condensations is parallelized on the GPU, making this process significantly faster. And in step 4, when we extract clusters, the cluster selection is fully parallelized on the GPUs. And the last step, the GPU-based computations speed up convergence, making the algorithm highly scalable. And on the next slide, we provide a code snippet to visualize the HDBSCAN using cuML UMAP. We start with the cuML loader on the top. Then we perform the HDBSCAN clustering using cuML. And afterwards, we reduce the dimensionality to 3D using cuML UMAP. Here comes another notebook. Not sure if you guys have finished the execution of the DBSCAN notebook. So we are going to spend another 15 minutes on HDBSCAN. Let me set up the alarm. But I would like to give you a high-level walkthrough. This one may take less time to execute. Like here, I'm only selecting 10,000 dataset size. just for the purpose of this workshop. But in reality, I usually choose at least millions of samples for machine learning tasks. And here I'm using both persistence score and the SQL score to identify the optimal value for mean cluster size. And after I identify the best value for mean cluster size, which is a hyperparameter, I input it back to the original machine learning algorithm to visualize the result. So you guys may be able to run the two notebooks at the same time. It may save you some time. Okay, let's get started. We have 15 minutes. Hi. Looks like we all come back, but we can take another 10 minutes break if you want. I'm just rushing it through so I can return you some time back in the end. Okay, let's get started with the next section, hyperparameter optimization, HPO. Here we are using Optuna combined with cuML Desk to run multi-GPU HPO experiments. Step 1, we need to set up a CUDA cluster. Here we are using Desk to set up the client. If you have only one GPU, your n_workers is going to be 1. But if you have multiple GPUs, you're going to have multiple workers. If you have one GPU but multiple nodes, you're going to have multiple workers as well. Step 2, we are performing training and evaluations. As this is a clustering algorithm, we're using silhouette score as the evaluation metrics. And step 3, the objective function. We design the objective function and suggest a range of possible values for each hyperparameter. Here I'm using a k-means example. I'm going to suggest a range of possible values for hyperparameters for k-means, including n_clusters, init, max inter. And in step 4, we are performing HPO trials and study. For example, we can start a 200 trials. And in step 5, we visualize the outcome. And the outcome is you can actually design your outcome. The outcome I'm using here include the best params, best silhouette score, and number of finished trials. And for different algorithms, we have different hyperparameters. The top three hyperparameters for k-means include n clusters. It defines how many clusters the algorithm should create. Init controls how initial cluster centers or centroids are chosen. Options include k-means ++, random. And max iter, the maximum number of iterations k-means runs before convergence. As for DBSCAN, the top 3 hyperparameters include epsilon, mean samples, and metric. Epsilon measures the maximum distance between the two samples for them to be considered as in the same neighborhood. Mean samples is the minimum number of points required to form a dense region, for example, a core point. And metric is the distance metric. By default, it's Euclidean. And other options include Manhattan, cosine, etc. As for HDBSCAN, the top 3 hyperparameters include mean cluster size, mean samples, and metric. For mean cluster size, it's the smallest number of points required for a group to be considered a cluster. The mean samples defines how many neighbors a point needs to be a core point, and metric defines how distance between 2 points are measured. For example, Euclidean by default, Manhattan, and cosine. This piece is very similar to HDBSCAN. So let's get started with your HPO notebook. And you can also monitor your hyperparameter optimization progress on the dashboard available in the URL. I believe the point number is 8050. Let me give you 15 to 20 minutes to try this notebook. If you have any question, I'm going to be around. bird topic. Bird topic. Bird topic is a real-world use case for HDBSCAN. The bird topic is a topic modeling technique that uses transformer-based embeddings to identify and cluster topics in large text datasets. Unlike traditional topic modeling techniques like latent dirichlet allocation, LDA, which relies on word frequency distributions, bird topic leverages a pre-trained language model such as BERT, Roboter, or Disk2BERT to generate document embeddings, making it context-aware and more accurate for clustering similar topics. And I draw a diagram showing bird topics workflow. We start with the raw dataset, then we use transformer to convert it into embeddings. Then we create two instances, UMAP and HDBSCAN, and we pass these two models to bird topic model, and we get the clusters. And why do we need cuML for bird topic? It's because bird topic relies on dimensionality reduction UMAP and clustering HDBSCAN to extract meaningful topic groups. The standard, like CPU-based UMAP and HDBSCAN, can be computationally very expensive and slow, especially for large datasets. Using cuML's GPU-accelerated UMAP and HDBSCAN, we drastically reduce the processing time while maintaining the same cluster quality. As you can see on the bar chart on the right, the overall time elapsed for bird topic, fit, and transform functions has been reduced by 90%. And from the coding perspective, we start by loading the cuML, dropping on the top. Then we load different libraries. Then afterwards, we load the IMDb movie reviews dataset. And then we create instances of GPU-accelerated UMAP and HDBSCAN. And afterwards, we pass the above two models to be used in bird topic, and we create the visualizations in the end. The visualization on the right-hand side is called intertopic distance map. It shows how topics are distributed in a 2D space. Each circle represents a topic, and its size reflects the topic in importance. Like larger circles indicate more significant topics. If the topics are far apart, then they are distinct. If they are closer, they have overlap meanings. Now let's get started with the bird topic notebook. I think I'm just giving you 10 minutes because bird topic is relatively simpler and easier to understand. Maybe let me just give you a high-level walkthrough. I already explained the code in the first section. And afterwards, we can use getTopicInfo method to get the topic ID and the respective top keywords. Then afterwards, we can get detailed keywords for each topic, and we can map documents to their topics. Now you have 10 minutes. Also, bird topic actually has a lot of fancy visualizations. If you are interested, you can, I'm not asking you to follow my LinkedIn, but I create a lot of fancy bird topic visualizations and post it on LinkedIn. Let me show you one. I think this is going to be interesting to show. Here you go. And this is one of the bird topic visualizations using data map plot. As you can see, when you zoom in, you can see like even the detailed review text message there. Also, the continent is just giving you like how the clusters are spread out. That is very cool. And the code is just available here. You can refer to the code here if you are interested in plotting the similar things. We have 8 minutes left. right on time. This is the last piece of our section. The talk, the presentation piece. We're going to do an in-depth comparative analysis of k-means, DBSCAN, and HDBSCAN. You may wonder when to use which, right? So let's go start from the advantages, disadvantages, and the real-world application perspective. As for k-means, it's the simplest clustering model. It's simple and very fast. It has disadvantages, like it assumes a fixed number of clusters, and it's very sensitive for the initializations, like how you initialize it. The initial values you pick for k-means matters. And its real-world applications include customer segmentations, color quantizations. As for DBSCAN, unlike k-means, it does not require you to have a predefined number of clusters. It can detect arbitrary shaped clusters, and it can do automatic noise reduction. In other words, it's pretty good at handling noise. It has certain disadvantages, even though not so obvious. It's sensitive to hyperparameters as well, epsilon and mean samples. And it just assumes a fixed number of epsilons for all the clusters. And it's not very effective in varying density clusters. So if you have a cluster that has dense data points and it has relatively looser data points, it will not work well. And its real-world applications include fraud detection, geospatial data clustering. And as for HDBSCAN, similar to DBSCAN, there's no need to specify the number of clusters, and it's even more robust in handling noise and outliers than DBSCAN. And it can identify clusters of different densities and shapes, as opposed to DBSCAN. DBSCAN is not effective in varying density clusters, but HDBSCAN is. Because for its different hierarchical clusters, it will assume different densities and shapes. And it has disadvantages. Like its algorithm is super complicated. It has a higher computational complexity than any other clustering algorithms. And its real-world applications include anomaly detection, typically. And some of the key signals from k-means that will tell you to go to DBSCAN or HDBSCAN. First one is when the clusters are not spherical. So k-means will assume all the clusters are in spherical shape. When they're not spherical, we would like to take the density-based approach, some algorithm that can detect arbitrary shaped clusters. And DBSCAN or HDBSCAN is better choice. And when the clusters have varying densities, we'd better pick an algorithm that can automatically adapt to cluster density. In that case, HDBSCAN is the better choice. And when we have too many outliers or noise, which is pretty common when we are doing some language like topic modelings, we need algorithms that can handle outliers and noise well. When that happens, we prefer HDBSCAN because it's very robust in handling outliers and noise. And last one, when the number of clusters is unknown, we need a cluster that there's no need to predefine number of clusters. DBSCAN or HDBSCAN could be better choices. And talking about the use case, from the use case perspective, when the dataset is GPS or geospatial data, we usually recommend DBSCAN because geospatial data is often arbitrary shaped. When it comes to text embedding clusters, For example, when we are doing topic modeling, we would recommend HDBSCAN because text embedding is usually high dimensional with varying densities. And when it comes to image similarity or embeddings, we recommend HDBSCAN combined with UMAP, as HDBSCAN is robust to different densities and shapes. When we are doing customer segmentations, we recommend k-means because the clusters are spherical and similar in size, right? And the business usually want a fixed number of clusters. For example, like when we want to do a customer segmentation for different risk levels, we only want 4 categories: customers of high risk, medium risk, and low risk. And when it comes to image color quantizations, we recommend k-means. And why? Because colors naturally form compact spherical clusters in RGB space. But again, I feel like instead of looking into the use case, we should focus more on the underlying patterns and characteristics of the raw data. And from there, we are picking different algorithms. And the last lab is exercises notebook. It's a long notebook. I have been using Amazon All Beauty Reviews dataset. And I can give you a high-level walkthrough, but before then, let me tell you something about NVIDIA's developer program. So we have very good developer program at NVIDIA. We care developers a lot. We publish a lot of technical contents. If you want to keep track of what is the latest, what's going on in the data science ecosystem, and new techniques introduced in our framework and libraries, you can go to developers.nvidia.com and sign up for the newsletters. And also, we have some free technical training. You can scan this barcode and check out our accelerated data science learning path. And there is even discount of the exams or certificates we have. This event called SciPy as 50 is valid till the end of the month. Now let's go back to the exercises notebook. And I'm going to give you a high-level walkthrough. First section, environment checkout. And the second piece is data loading. For this exercise purpose, we use Amazon All Beauty Reviews dataset. We put all the reviews tags into a single list, and we do data pre-processing. And then we use this transformer to convert it into embeddings. And then we perform the dimensionality into 20 dimensions. It may take some time to load. If you have memory issue performing the dimensionality using UMAP, you can directly import the reduced data DF dataset from the data folder. I'm already providing the dataset in CSV file, and we are going to use the last 20,000 rows for the purpose of this, for the machine learning exercise. Then applying the cuML k-means clustering using this dataset. First step, I'm identifying the optimal number of clusters. Then I dump it into the k-means clustering models. And I visualize the clustering results using UMAP in a 3-dimensional space. Similar thing I did on DBSCAN. First, I identified the optimal number of epsilon using the approach grid search, and see whole vet score. Then I dump the best value of the hyperparameter into DBSCAN, then I visualize the 3D scatter plot. And the similar things I did for HDBSCAN. That is all about this exercise notebook. So the rest of time, feel free to practice. If you have any questions, just let me know. I can go to your desk. Or if you want to have a conversation with me, feel free to ask me any questions. Yeah, my colleague just reminded me. We NVIDIA have a reception event on Wednesday night. You guys are all invited. Welcome. In the Museum of Glass. Yeah, if you have any questions about this workshop notebook after this workshop, just feel free to send a message to me on LinkedIn. Also, if you want to get connected with me, just add me on LinkedIn.